A couple of weeks ago, we learned about a discovery made 200 years ago, almost 200 years ago to the year, by Hans Christian Ørsted. He said in 1819 that electricity generates magnetism, or electric current, moving charges, electric current generates a magnetic field. And we said at the time that that was, well, at least in my mind, one of the most, if not the most important technological discoveries ever. Now, we fast forward 12 years, still early on. We're still almost 200 years ago, right? 1831. Two guys, Faraday and Henry, we talked about this one a little bit yesterday, independently discovered that magnetism can produce electric current. So essentially the opposite of what Ørsted said. But there were conditions put upon this. Ørsted's discovery, there were no conditions. If you have an electric current or moving charges, it would, in every single case, no exceptions, generate a magnetic field. But a magnetic field would produce an electric current only if one of three conditions were met. You've got to have a conductor, and you've got to have a magnetic field. In order for the magnetic field to generate an electric current, you either have to have the conductor move or the wire move relative to the magnetic field. So here's the magnetic field. It's a constant magnetic field caused by two bar magnets. There's a wire in between them. That wire has to move. Or if the wire remains stationary, the magnetic field could move. So you could move the magnets themselves. Doesn't really make any difference, right? You ever find yourself sitting in a parking lot waiting for your parents to come out of a store because you don't want to go in there? You just kind of, I'll sit in the parking lot and kind of snooze for a few minutes, and then you kind of wake up when the car beside you is backing up, and like it feels like your car is going forward. Do you ever notice that? Right? It's relative motion, right? Like we perceive the exact same thing, whether that car is moving, the car beside us is moving, or whether our car is moving. Our perception is exactly the same. It doesn't matter, in the end, which one is moving. Our brain, for a short time, interprets it the same way. Well, it's kind of the same deal here. If we have a wire that moves through a magnetic field, great. If we have a magnetic field that moves around a wire, great. It ends up being exactly the same effect. We generate an electric current in both cases. Now, there is a third one as well. We'll put a little line in between the second one and the third one, because the third one we don't really use in Physics 30, but it's just one of those things that's there. If we have a changing magnetic field, so in other words, the magnetic field increases or decreases, or increases then decreases, or whatever, then we would generate an electric current as well. Again, our focus in Physics 30 is going to be on the first two, either moving the wire around the magnetic field or moving the magnetic field around the wire. Now, we started learning yesterday at the end of class after a little demonstration where Matt was dropping a little piece of steel through a copper tube. Everybody else is dropping a little magnet through a copper tube. We learned that there is potentially an interaction between these two discoveries. And that third kind of complementary discovery that kind of complements or supplements Ørsted and Faraday's discovery, was made by Lenz. Lenz said that, yeah, Ørsted and Faraday are both right, but what's caused by one can actually cause the other. So Lenz said, basically, Faraday's correct. When a magnetic field, we'll call it B1. Okay, we're naming this magnetic field that we have. In our demonstration yesterday, this would be the little magnet that most of the people in the demonstration dropped, except Matt. Magnetic field number one and a conductor move relative to one another, whether it's the magnet that's dropped or whether it's the conductor that's dropped, it doesn't really matter. You're going to generate an electric current in the conductor. That's Faraday. Well, we also said that Henry discovered that as well, although usually we give credit to Faraday, or more credit to Faraday at least, for some reason. So now we get an electric current that we didn't have before. That electric current, that's the generator effect, by the way, right? We've just taken motion and changed it into electricity. Well, Oersted taught us that electric current generates a magnetic field. That's the motor effect. If we combine the generator effect and the motor effect, then we get what happened yesterday in our demonstration. Moving magnetic field yesterday generated a current. That current generated a magnetic field. Well, by the end of it, we had two magnetic fields. The original one, that's the one that we dropped, the little magnet that we dropped, and the one that was produced by the current. Two magnetic fields. Now, those two magnetic fields acted together to oppose the motion. Do you understand what's happening here? Magnetic field number one causes by the generator effect current, and then that current by the motor effect causes another magnetic field, and then those two magnetic fields act together to oppose motion. Whether it's the magnet that's moving or the wire that's moving, the motion of whatever it is that's moving will be opposed by these two magnetic fields acting together. You got two magnetic fields, they've got to interact with each other. And we know by the law of conservation of energy, then they're not going to interact with each other to help the motion. If Matt was the person that dropped the steel yesterday, who dropped the magnet yesterday? Okay, Cameron, Kessler, Cameron, a few people dropped the magnet yesterday. If Cameron had to drop the magnet and that magnetic field caused a current, which caused a magnetic field that helped the motion of that magnet, then all of a sudden that magnet wouldn't have accelerated downwards at about 1 meter per second squared. It would have accelerated downward at about 20 meters per second squared. So we would have had a certain amount of potential energy at the top before Cameron dropped it, let's say 10, and then we would have had even more kinetic energy at the bottom after it reached the bottom, let's say 20. Well, how do we get 20 joules of kinetic energy when we only started with 10 joules of potential energy? That can't happen. So we know there has to be an interaction between these two fields, and it has to be an opposing interaction, otherwise it would violate that law of conservation of energy. We'd be creating energy from nothing. So let's take a look at a couple of situations where this Lenz's law thing could apply. We saw that in our demonstration yesterday, but we didn't do a formal analysis of that demonstration yesterday. So let's do that now. Let's say that we got a magnet, and that magnet has two poles, of course. Let's make it a south and a north pole. Let's say we've got a coil of wire that looks like this. It's not attached to a battery. Rather, that coil of wire is attached to, could be any kind of load, like a light bulb or an electric motor or whatever. This is the symbol, by the way, for a light bulb. You don't need to remember that. Okay, I'm just showing you that there's a light bulb in the circuit. What's going to happen to this light bulb right now? Nothing. The light bulb is not going to light up. If you're 5 years old and you have a light bulb and you have wires, you might think that hooking the wires up to the light bulb somehow might cause the light bulb to light up. But if you're any older than that, you know that you need some kind of power, a battery or something to make the light bulb light up, right? We know if we're more than 5 years old that this, as it stands right now, is not going to work. The light bulb will not light up. But let's do this. Let's move this magnet. Let's push it to the right. Like we may push it to the right with our hands, or there may be some kind of wind that's blowing it to the right, or some kind of current, water current or something that's moving it to the right. It doesn't matter what's causing it to move to the right. We've got kinetic energy in this magnet. It's moving to the right. What did Faraday say would happen if you've got a magnet and a wire, and the magnet is moving? It would create not a charge, but a current. Yeah, close. It would create a current. Now, we could have just as easily moved the wire and we would get the same effect, but I'm just choosing to move the magnet here. So I'm moving the magnet to the right. That will generate a current in the wire. Which way does the current go? Don't know. But we know there's a current there. What did Oersted say that current would do? Produce a magnetic field. So now we've got two magnetic fields. We've got the one that was caused by this magnet, this north-south magnet, and now we've got this new magnetic field that was induced in this solenoid. What do you think the polarity of it is? As this coil or this solenoid becomes a magnet, as a result of the current that was caused by the moving magnet in the first place, it's going to have a polarity, a north pole and a south pole. Which end do you think is going to be north? There was a key word in this whole Lenz's law that's going to tell us which end is north. Brandon?
Is it going to be the left side?
Is north?
Yes.
Absolutely. Yeah, the left side is north, and the right side is south. How do we know that? Brandon, how did you know that? Because it has to oppose the motion. If I'm moving this permanent magnet to the right, the only way to oppose its motion is to have a force of repulsion pushing it to the left. Does that make sense? All right, we know the magnetic field inside the coil goes from south to north. Outside it would go from north to south, but inside, south to north. We take our little manipulative that we made here a week ago. We stick our thumb in the direction of the magnetic field. This is the coil roll now, right? Thumb in the direction of the magnetic field, which is south to north, means it points to the left. Fingers in front are going to point downwards. So that means the electric current in this wire is going to point down in the front, like this, or up in the back. Does the light bulb light up? You got a current going through it. Sure it does. If you move the magnet through the wire or relative to the wire, you're going to generate a current that's going to go counterclockwise here that's going to cause this light bulb to light up. Now, let's draw another one that's almost exactly the same. Once again, we have our south pole and we have our north pole. Once again, we have our solenoid that looks like this. And our light bulb right here. This time, though, we're moving the magnet this way. We're moving the magnet to the left. What did Faraday say this magnet would do? We got a magnet, we got a wire, we're moving the magnet. Faraday said that would make a current. There's a current in this wire. Which way? We don't know. But there's a current in this wire that generates a magnetic field. Another magnetic field. A second magnetic field. And that magnetic field must, Nick, oppose the motion. All right. So what's the polarity of this solenoid going to become if it has to oppose the motion of this? Tell me, which end is this, north or south? This is going to be south and north this time. South, because the only way to oppose this magnet's motion to the left is to attract it back to the right. Notice we said when we said Lenz's law, we said the two magnetic fields act to oppose the motion. We didn't say they repel. We said they act to oppose the motion. Sometimes, as in the first diagram here, opposing the motion means repel. Sometimes opposing the motion means attracting. Okay, so if this is the south pole and this is the north pole, the magnetic field goes this way. We would stick our thumb to the right. Fingers would go in front of the coil, they would go up. So we would have an induced current up in the front, down in the back. So in this case, it would go clockwise. Now, somebody in the last class stuck around after class for a moment and asked me what I thought was a great question. And this, in effect, was the question. He said, what would happen, basically, if you pushed the magnet through and then it got halfway through and started going out the other side? Like so, let's go back to the first diagram. I'm pushing this north-south magnet through. It gets halfway through, and now it's coming out the other side. What do you think is going to happen there? The polarity will flip. And if the polarity of the solenoid flips, then the direction of the current will flip as well. So basically what you've got there is alternating current. That's what we use in our houses, alternating current. Current that goes back and forth. Okay, if we have a magnet that's being pushed this way, cause the current counterclockwise, as soon as it gets halfway through, then we end up having to have a north pole over here to attract it back. And the polarity flips, and therefore the current flips direction as well. Make sense? Okay, that's what we have with an AC generator, okay, an alternating current generator, which is, for the most part, how we generate electricity. You got water going through a dam, turns a turbine, generates AC current, alternating current, because one moment you've got it going this way, one moment you've got it going this way. It just alternates it several times per second, that's all. Okay, does that make some sense? I believe you got a couple of questions, 2 or 3 questions in your unit assignment that relate to this. This is the last thing in the unit. So now you guys should be okay to finish off that unit assignment. Tomorrow, it's not due tomorrow, but you can feel free to ask me questions about it tomorrow. We'll probably end up starting our new unit tomorrow. Just come with your questions about that assignment or anything else related to Monday's test, right?